Hello, this is the Big Data course. In this part of the course, we're going to focus on some technology we've already discussed, namely k-means clustering, with a little different angle in that we're actually going to be running some particular Python code to illustrate k-means in action, whereas previously we didn't actually discuss the detailed implementation. And of course, k-means is just a particular data analytics, and so forms part of our motto of using clouds, running data analytics collaboratively, processing big data to solve problems in X Informatics. All right, k-means in Python. Um, this can actually be done in multiple ways. We've used this book by Harrington in the past. However, although chapter 10 of this book has a good discussion of k-means with some interesting examples, we will not go through that in this course, but rather use the built-in support of k-means in the SciPy package, and we will actually modify that software. Here is a link to the software. There are multiple functions there. It's labeled VQ for vector quantization, which is one of the utilities that we actually use in the k-means application to associate points with clusters. And I also give the link to the documentation page for the k-means algorithm. There are 4 files provided with this section. The file k-means extra.py actually we don't run in this class, but it's useful there. It invokes the actual SciPy code. It calculates it does clustering based on the fake data, which fake data is actually used in a later file, parallel k-means.py, which generate 4 actual clusters of 3 different sizes, small, large, and very large. The file we will use uses a modified k-means code with various enhancements to allow me to illustrate some points. Those modifications include map-produced parallelism, which we won't discuss immediately, but in a later lesson. And it generates, every time you run it, 8 plots by doing clustering of this data set into 2, 4, 6, and 8 clusters. We will demonstrate using this software in this lesson. There's also another piece of code, which is the one we'll start with, xmean.py, which uses the SciPy built-in k-means, and it reads data from a CSV file, and it does a very simple clustering from a CMU class I found on the web. So this is the CMU example. We have 85 records. It's in a CSV, namely comma-separated file, and that file is available to you as a resource. And we're trying to, it just lists weight and height, and we're trying to divide it into various clusters so we know roughly what the good sizes are to make for our t-shirts. And we can, this particular not totally general code can go from 2 to 5 clusters. The k-means code will cluster into any number of clusters, but the plotting program only plots up to 5 clusters. So here's the type of thing you get if you run this data, which is here plotted using matplotlib, of the weight, which is the y-axis, and the height, which is the x-axis. You get a sort of linear, broad linear distribution. So it runs up here in a nice linear curve. Then if you cluster it into 2 clusters, you get the small t-shirt here with this as the center, and the large t-shirt here with that as the center. If you then just rerun that with k of 3, then you will get the small, the large, and the very large, or whatever, however you want to label them. And So that's illustration of running it for two values of k. Let's just do that for real. So what do we do here? We better find the code, which is sitting here. Here's xmean dot py, and you have to feed in the value of k, and the value of k is set to 2 here. Well, we showed you k equals 2 and 3. Let's do k of 5 to get something a little more interesting, and we will copy this code, Control A, Control C, and then we put it into our IPython window. Here it goes. And we get the answer. It's very quick. It's only 85 records. And that's not actually very big. Let's see if we can make it bigger. Here we are. The black squares are the centers. 1, 2, 3, 4, 5. And then we have green, blue, red, yellow, maroon as the colors of the clusters. And so obviously we've taken this broad distribution and chopped it up into 5 components. And we could, I already showed you k of 2 and 4, 2 and 3 in the slides, and you can obviously let you run k equals 4, and you can also modify the code to run larger values of k, or maybe you can find some more data to do something similar with. So this is a really straightforward, run-of-the-mill, basic use of k-means. Okay, let's go back to the PowerPoint. Okay, so now we go to the case where we, which is actually a common thing to do when you're clustering. You want if you're trying to develop a nifty new clustering algorithm, it's good to know the answer. So we generate here 4 clusters. Each of them has 250 points. The 250 points have a bell-shaped distribution, which is the Gaussian distribution, which we already discussed at length in the physics part of the physics Higgs particle analysis part of this course. And we fix the centers and the radii, with the radii being the standard deviation of these clusters. So the 250 points are randomly generated. They'll be different each time you run the program, because remember, Python does not always use the same starting point. And we have 4 centers, basically at the corners of a square of side 3, starting at the origin and going up to the position 3, 3. And the basic set of 4 clusters, which are called the large set, have radiuses 3/8, 0.55, 0.6, and 1/4. And those, I say, are large. Then the larger 2 of these clusters are these 2 here, 0.55 and 0.6. Those 2 are at the top at y equals 3. And there is no significance in the fact that the radii are slightly different. They're just what I thought of one day when I was writing the code. And we generate 2 other cluster sets, the so-called small clusters, which have a radius which is exactly 1/4 of this. And we have the very large clusters, which have radiuses which are 1.5 times these values here. Now let's remember what k-means does. We have a set of points. We want to find a specified number, k clusters for those points. We choose a random starting point. So we choose, typically what you do when you have a set of points is you don't generate the centers randomly in the space. You just take actual k of the points, leaving n minus k not to be centers and k to be centers. This at least ensures that your centers have to be at least near 1 point, because they're exactly equal to 1 point. Then we iterate the algorithm. where we associate points with the cluster. That's what's done with the utility VQ, vector quantization. And then we calculate the new center positions as the centroid, or the average of the points associated with each cluster and its center. And as I said, Python has a k-means code which we will use. And as the source is online, I gave you a link. We can change that code for our own satisfaction. And we will do that to illustrate parallel computing in a later lesson. And here we will make a small modification to the quality criterion, quality of fit of clustering criterion, which I call the goodness criterion. And here we write out the k-means algorithm again, and it's notice we have to do a calculate. This is actually what's explicitly implemented. We do have to calculate the point center distances. This is called the distortion. We do have to delete zero-size clusters, and we do have to check conversions. And another point about this slightly more detailed algorithm is we do an iteration over the starting positions for the cluster centers. There is a parameter which in the defaulted to 20 in the Python code for the number of such iterations. We will actually run it with different numbers for that iteration. Typically 1, because we want to show what happens when you get trapped in the local minima and you do not actually necessarily get the best solution.